So, I direct the Spatiotemporal Machine Learning Lab in UC San Diego. The mission of our lab is to advance machine learning for large-scale spatial temporal data and decision making. There's a lot of information in space and time, ranging from climate science to public health to transportation and many other engineering and science disciplines. So, if we can successfully understand the meaning in the space and time data and being able to reason, that will be fundamental to lead to the advancement for real-time decision making in science and engineering. So, deep learning is undoubtedly the most powerful model in processing large amount of information. However, it's still very limited in understanding information in space and time because compared to traditional applications in machine learning, such as static images or discrete text tokens, space-time data is fundamentally dynamic and it's also continuous valued. So that drives a lot of new challenges in machine learning. My research aimed to address these fundamental limitations in deep learning, specifically for space and time reasoning towards real-time decision making. And I will talk about three research themes that has been occurring in our group to address those challenges. The first one is a lot of the space-time data is generated by physical systems with underlying governing equations. So how can we inject principled physical laws into the design and training of these deep learning models? And our group has spearheaded this area called physics-guided deep learning, where the idea is to integrate first principles with deep neural networks such that these models can generate much more trustworthy predictions. Secondly, for space-time data, there's a very complex interactions, whether it's from different variables or different space locations or time points. So how can we capture this type of a relationship in high-dimensional spatial temporal data and even infer causal relationship from them? That's another challenge, especially in the context of deep learning. It's very difficult to provide their identifiability results for causal discovery output. And finally, for space-time data, we also need to understand the confidence intervals of the prediction, especially for forecasting. So to properly calibrate the uncertainty model is another key challenge in space-time learning. So for deep learning, we know that they're very good with generating point estimates, but they often tend to be overconfident in the forecast. So how can we tackle this kind of challenge in the context of probabilistic deep learning? That's the overview of today's talk. And then for each of the theme, I will give you some examples of our research in the field, and I will give some high-level vignette of what has happened in the scope. Feel free to type questions on the chat, and I'm happy to address them at the end of the talk. So first, let's start with injecting physics. We know that deep learning are data-driven models. So deep learning models don't have a framework of physical reasoning, and they often generate scientifically unrealistic predictions. So how can we ground these deep learning models with physical laws is what I'm interested in. In particular, let's look at this example of forecasting climate. We know that weather and climate often cases rely on very expensive numerical simulations. So it'd be great if we can develop deep learning surrogate models that can mimic the behavior of this complex numerical simulation, but significantly accelerate the speed of forecasting and scenario creation. So if we turn this problem into a machine learning task, fundamentally, we're trying to learn the conditional distribution of the states, which is xt to xt minus L, and that's the past states of the weather or climate. And then our goal is to predict the future sequence of states, xt plus 1 to xt plus h. And we're learning this conditional distribution, hoping that the model that we obtain can give us properly calibrated uncertainty. And here, xt is a state of the climate system, so it can include multi-variables like temperature, precipitation, or wind, etc. So a lot of the existing models for climate emulation is deterministic, and they cannot capture the uncertainty well, and often cases they're not physics informed. So the challenge here is that data is extremely high dimensional. We're looking at essentially a video of several hundred thousand of dimensions, and then we wanted to long-term projection of the climate, and then underlying dynamics of the climate is highly nonlinear. There's a famous phenomenon called the butterfly effect, which describes that. So we use build our technology based on this technique called diffusion model. This is the state-of-the-art generative model in machine learning. The idea of diffusion model is that they first add Gaussian noise to each step of the diffusion, and this process is called the forward process. By degrading the image data into some white noise, we can actually reverse the process to learn a reverse modeling that turns the noise into data. And this process actually is completely learnable. And that's the high level idea behind diffusion models. So one of the limitations in diffusion models is that during the forward process of adding noise to the data, it's simply just adding Gaussian noise. And at each step during this degradation process, the intermediate steps are completely thrown away. And for forecasting, we actually want to save all these intermediate steps so that give us much faster sampling algorithm for diffusion models. And I also want to mention a lot of diffusion models were designed for only for static image data and then not for physical dynamics. So we proposed a model called diffusion, a dynamics-informed diffusion model specifically for spatial temporal forecasting. This was a newspaper in 2023. So as I mentioned before, the top row shows the existing diffusion model where you iteratively add noise to degrade the data and then reverse that process to generate data from noise. But then this procedure ignores the intermediate steps during diffusion, so it can be very slow for high-dimensional sampling problem. We propose a diffusion. The idea is to rather using a data-driven data degradation process. So instead of adding Gaussian noise to the data at every step of diffusion, we use a data temporal interpolator, which is another neural network. This neural network is trained from data, so it's dynamics informed. It learns to degrade data step by step. And then all these intermediate states during diffusion actually can be used as intermediate forecast. And this significantly reduces the computational complexity, memory footprint, data efficiency, and then it reduces the number of diffusion steps. So this is the animation, shows how diffusion works. It iteratively performs interpolation with a data-driven interpolator network, and then forecasting, which is another neural network. So these two neural networks intervene with each other to save all the intermediate states of diffusion. And then we actually can prove this model is implicitly solving an ODE shown in this bottom form. So the interpolator and the forecaster give the solution to this ODE, and then the state-of-the-art diffusion model based on DDIM, which is a deterministic degradation process, actually models a slightly different dynamics. So as results, what you're seeing is the forecasting performance of the ground truth, the baseline model based on Monte Carlo dropout, and then our model diffusion. And this is for the forecast of fluid Navier-Stokes equations. And you can see that the model can actually capture the intricate flow patterns in the Navier-Stokes equation. And then it also can capture small scale dynamics much better than the baseline. The bottom table shows the forecasting performance for sea surface temperature, which is the climate forecasting benchmark, and Navier-Stokes equation forecasting results. So we're specifically looking at diffusion, which is our model, compared to one of the state-of-art baseline, MCVD. So MCVD is a diffusion-based video generation baseline developed out of OpenAI, and it basically utilizes a transformer-based backbone with a classic diffusion technique. And this model can get pretty good generation results in terms of CRPS and MSE, but it's very slow. And our model actually can match the generation fidelity in terms of the CRPS and MSE, but it's almost 20 times faster. than state-of-the-art diffusion models. So that shows another example how we can add physics to the diffusion model and accelerate sampling. We further extended this idea to generate an emulator for global climate. And then in order to take care of the spherical geometry of the Earth, we replaced the backbone from the previous diffusion model from a UNet to a spherical Fourier neural operator. So a spherical Fourier neural operator essentially uses spherical harmonics to capture the spherical geometry of the Earth. And then the sampling procedure is exactly the same as our diffusion framework. This paper won the Best Paper Award as ICML Machine Learning for Earth Science Modeling workshop. It was presented at NERSC in 2024. It was a collaboration with a group of climate scientists in Allen Two Institute. So with this model, we were able to speed up the physics-based climate emulation by 25 times. On the left, you're seeing the video of the simulation from a physics-based model. And then in the middle and the right are the samples from our diffusion model. And you can see because the model is stochastic, so we can draw multiple samples from the model, but the turbulence that the dynamics that the model has learned perfectly emulate the physics-based model. So a nice thing about the probabilistic emulator is that we can generate a lot of samples and calculate the ensemble average. This is actually very important to calibrate the forecasting uncertainty of climate projections. With this model, we were able to generate 100-year stable rollout for global climate at 6-hour resolution. And then the gray bar in reference here for surface pressure, total water path, and the reference is you can see that our model has the lowest error compared to reference, which is the physics-based simulator, and is actually 70 times more accurate than the state-of-the-art emulator for global climate. So in general, we have been working intensively in this area called physics-guided deep learning. We have various techniques to inject physical knowledge into the design, the optimization, and training of these models. One of the highlight of our work is this idea of using symmetry as an inductive bias to build neural networks. So by symmetry, I meant like a function that is commuting with this group action. So if I have a velocity field and I scale it by 2 plus in terms of magnitude, and I rotate the velocity field by 45 degrees, it will give me the same result if I rotate the velocity field by 45 degrees and then scale. So this kind of commutation between the function operation and the group action is known as a group equivariance. So it's a type of symmetry for the function. So the idea of injecting symmetry into deep neural network is to build neural networks that actually can preserve this type of property. And the idea is to generate generalized translation symmetry in CNNs to any other group. So in CNNs, the reason we can have translation symmetry is that these orange blocks in the filters are exactly shared. So this is a scheme called weight tying or weight sharing. We can actually extend this idea to any group transformation. And this is what's showing in the bottom figure. When we try to predict ocean flow with different type of scales, if the model is not aware of symmetry, you can see the error in gray bar actually explodes as the data shifted away from the training set. But if the model is aware of such symmetry, then the performance is very robust regardless of how we transform the test data. Furthermore, we can inject the symmetry in the latent space. Then when we build models to emulate complex fluids with a different buoyancy factor, the model is able to still generate realistic high velocity flows compared to a baseline that just completely failed in this case. We actually have a survey paper published at PNAS that outlines this general framework of physics-guided deep learning. It's written by me and my students, so I encourage you to check it out. The second part of this talk is about modeling interaction. Because space-time data is hyperdimensional, there exist complex interactions in both space, time, and different covariates. So how can we extract this kind of interaction? Most times are latent from observational data. So we're looking at specifically this problem of causal discovery, and specifically for time series data. This work was published in ICML 2024. Um, in this task, we are given a set of time series. So, an example here is the stock price of different companies, Apple, Amazon, and Microsoft. The stock price vary across different quarters. So, we wanted to discover whether there's hidden causal graph for different type of company stocks, whether the Apple stock is actually driving changes to Amazon stocks, and so on and so forth. So we want to build a deep learning model that can discover causal structure directly from observational data. But we also observed that a lot of the real world data is multi-model and heterogeneous. So a lot of the existing methods assume there's only a single causal graph for the entire data set, which is quite limiting. So in this paper, we ask a much more general question. Can we discover a mixture of causal graphs, assuming these causal graphs are different across different quarters? So can we discover this mixture of multiple causal graphs from data? The framework that we built our method upon is the famous structural causal model framework based on Judy Prof's the dual calculus. So given a structural causal model, in this case, we have three observational nodes, and that's x1, x2, x3. So the edges represent the causal dependencies. For structural causal model, typically we will derive the relationship based on structural equation, which is the variable xt is dependent on its parents and from the past, and also its instantaneous parents. And then the P of A as G represents the parent node of this variable xt in this graph G, and then noise is explicitly modeled in structural causal model. So in general, SCMs encodes causal relationships between variables. We know causal graph is a DAG, and it can be written with structural equation and noise. So in this case, we're specifically modeling lag parents and current time stamp, which is also known as instantaneous parents. The generalization of our assets from a single causal graph to mixture of multiple causal graphs is this idea of mixture causal discovery, or MCD. So here we're assuming there's latent and k different type of causal models, and the actual causal model for the data is drawn from this mixture of membership model. So for each nodes x of t, we assume it can come from potentially k different causal graphs, and for each causal graph, we will model it separately with structural causal equation and exogenous noise models. So to iterate, assuming we have time series and their d-dimensional time series, different variables, and we're looking at time series of t timestamps. So we assume they're coming from one of the k unknown SCMs. So the target output for our model is to figure out for each SCM, what is the underlying causal graph? So we're looking at a lagged time series. So L plus 1 is a lagged time series with an instantaneous timestamp. D by D represent the causal graphs between different variables. So we wanted to formulate this problem as a probabilistic inference task, where we wanted to infer the posterior distribution, which is the distribution over these hidden latent causal graphs M1 to K given the observational data, and the index 1 to n represents the number of examples. So total we have n different time series. So this is the model architecture of MCD. So specifically, the red one is the data, that's the observational data that we have. And then we take a variational inference approach to parameterize both the structural causal equation and the noise model. And because we're trying to perform in posterior inference over latent variables, so we're using essentially the evidence lower bound as approximation of the joint likelihood function. And then the parameterization of structural equation and the noise model are actually done through neural networks. So we can prove this model is actually identifiable under mild assumptions. So essentially, we want the model to be dominant in one of the clusters or one of the causal graphs compared to all the other graphs. So that's the ratio quantity that you're seeing, where we want particular one of the likelihood of the data belong to a particular SCM much larger than the summation of all the rest SCMs. So this kind of assumption is similar to clustering, where we want there's a cluster has at least one point whose membership is actually highly dominant compared to the summation of all the other cluster memberships. To verify this method, we basically started out with synthetic data, where the idea is that we can generate data based on known causal graphs. This is to verify that our model can indeed recover the true causal graph from data. And then we're looking at top row is where the functional relationship is nonlinear, and the bottom one is the functional relationship is linear. So the D is number of nodes, and then we vary the number of variables in causal discovery task. N is the number of examples, and T represent the timestamps. So we can see that for different number of nodes, our model, which is MCD, that's in orange bar, is the most accurate. It actually achieves 10 to 55% improvement over the state-of-art causal discovery baselines. So we're actually comparing with a large set of causal discovery baselines, including the classic PCMCI algorithms and VALIM, which is a sparse regression type of causal discovery algorithm, as well as deep learning-based causal discovery algorithms based on Rhino and Dino tiers. Just to show some fun example, we also showed that when we apply this data to the financial time series that I used to motivate the study, the model can discover interesting graphs from data. So graph 2 and graph 1, these two graphs are actually the two mixtures of causal graph that the model automatically discovered from data. So they actually change across different timestamps. So graph 1 shows that there's a very strong patterns within the industry sector of energy or real estate. And then there is some causal graph patterns between the energy and its own sector, but it actually pattern is reversed when you go to a different time graph. So how these kind of causal graph changes actually can map to the dynamics of time series. What you're seeing is the SP100 aggregated with time series over time. So the blue shaded area represent the causal graph number 1, and then red shaded area represent the causal graph number 2. So you can see whenever the model shift to a different causal graph, it actually corresponding to some dips in some dynamical changes in the time series that corresponding to the crypto crash in 2018 and the COVID-19 around 2020. So we extended a lot of this work to learn relational dynamics from data. One of the applications that we shown is we can actually build neural networks that can infer the patient zero from epidemic dynamics. So here the graph is the nodes are represent different compartments, and then the edges represent the commuting pattern in travel. So the goal of the task is to, given the current state of the epidemic, figuring out what was the original patient or compartment that was affected, a problem known as patient zero. We can actually show that based on this graph neural network idea, we can derive accurately the exact lower bound of recovery accuracy, and then the model's performance matches well with the theoretical guarantees as well. We extended the idea of MCD to spatiotemporal data. So what I've told you is how we can discover causal relationships with the identifiability conditions from time series data. And now if we're looking at spatiotemporal data, we have to deal with the high dimensionality problem in space. So here we're trying to discover the latent causal graph from high-dimensional spatial-temporal data. This paper actually is going to appear at ICML in a couple months, and then we can actually recover the known climate phenomena in high-dimensional climate data. So it actually uncovered regions that share similar weather characteristics and driven by these known teleconnection patterns, including the Northern Atlantic Oscillation and Antarctic Oscillation. So these are known climate phenomena in the literature, and without much knowledge in climate science, our model can recover these shared teleconnection patterns. Okay, finally, I will talk about the idea to imbue the model with the ability to quantify uncertainty, because we know deep learning models are very good with generating point estimates, but not very good with generating calibrated uncertainty. So getting uncertainty of the model is very important to estimate the risk of prediction and help decision making in downstream tasks. So the task we're looking at is, again, deep circuit modeling. So we want to build a deep learning model that can emulate the behavioral complex stochastic simulations, but much faster. So what people use for epidemiology modeling is this age-stratified multi-agent stochastic simulation. So using the simulation, you can ask what if type of scenario creation questions. Typically, you will say, how would the pandemic change if the policy of lockdown changes? Or how would the number of cases change in the next few weeks if we have a different virus variant? So this type of what if scenario creation questions have been traditionally answered using numerical simulations, but this kind of simulations is very, very slow. It takes about a week to generate one scenario. Obviously, it's insufficient for real-time decision-making needs in epidemic control and prevention. So we want to learn a model that can accelerate this process, but mimic the behavior of stochastic simulator. But as you can see, the stochastic simulation itself has uncertainty. So therefore, we want deep learning models to reflect this kind of uncertainty. So in the regime of surrogate modeling, Gaussian processes is a very common choice for surrogate modeling. The idea is we place a distribution on top of functions. Like in this case, I'm showing you the function of x times sine of x. So if we place the distribution on top of the function, and that leads to a Gaussian process, and the Gaussian process is parameterized by the mean function and the covariance matrices. So Gaussian process is known to struggle in high-dimensional data. So there's some work out of DeepMind that trying to generalize the idea of Gaussian process to deep Gaussian process or neural processes. So the idea is that we will use deep learning to explicitly learn the kernel function in GP, and then we will again train a lower bound, or evidence lower bound, to approximate the likelihood of the entire distribution. So the generation and the inference is done through encoder and decoder framework. It has some similar flavor as variational autoencoder, but it's actually learning the data-dependent kernel function for each data point separately. We extended this framework to spatiotemporal setting, and particularly we wanted to introduce the time dependency. So here we have the state of the system, which is the daily prevalence and incidence for each compartment in epidemic modeling. And then the parameter of the system is the initial condition at 0 and different parameters of the system, including the reproduction number, the contact rates, etc. Right? And then we actually induce this type of latent process to model the unknown dynamics in a system. On top of that, we introduce a graph representation learning component to encode the spatial interactions for commuting patterns. So to train this model, we basically have to generate a large number of simulations. And because the simulation is stochastic, we cannot afford to generate all the possible combinations of simulation data a priori. So instead, we take a Bayesian active learning approach where we iteratively generate simulation data on the fly. The idea is that we first train a neural process model to infer the latent process of the data. And given a new set of parameters, we'll use a model to predict in the on-scene regime what is the uncertainty of the model. So using an acquisition function, which is the criteria to select the parameters, we're going to select in the parameter regime, the current deep learning model is most uncertain. So that means we need more information to train the model in this set of parameter regimes. And then we will select this parameter regime to query the simulator again, and then we will generate a lot more training examples to feed that back into the deep learning model. So this kind of Bayesian active learning strategy allows us to save a lot of the training data and only generate simulations in the area that the model is uncertain. In terms of acquisition function, traditional acquisition functions typically is based on information gain. And because our system is very high dimensional, in fact, for this simulator, it has about 16,000 dimensions in terms of parameters. So if we compute the information gain in the input space, it will be too expensive. So instead, we propose this idea called latent information gain. But because we can infer a much lower dimensional latent space, now we can compute the information gain in the latent space, which is much more efficient. So we can show that this latent information gain is actually equivalent to the KL divergence between the likelihood and the posterior in the latent process. It can be computed efficiently and accurately for batch active learning. We can prove in this paper that using the idea of latent information gain And assuming the feature maps are random, we can actually significantly reduce the amount of training examples need to train this model. So if we use random sampling, which is a common technique for training deep networks, then we will have order of d squared divided by square root of t, number of amount of error. So for using a latent information gain based active learning method, we can significantly reduce the number of examples by order of d, where d is the number of dimension here in the input space, right? I mentioned in simulation we used is about 16,000. Okay, so here is a simulation that we use. It's a large scale stochastic spatial age structured epidemic model. It was developed by one of our collaborators in the field. It has about 16,000 dimensional parameters, has country level parameters, state level incidence, and prevalence compartment. So we'll generate about 300 scenarios, and that amounts to 16,000 sample sequences. Here is the result of our emulator compared to the ground truth. So the emulator is in orange, and that's a prediction from our deep learning surrogate model. We're looking at the prediction for different compartments, including infectious symptomatic, infectious asymptomatic, removed asymptomatic, or removed asymptomatic. So the ground truth is the output from the physics-based simulator, that's in blue. And you can see for most of the cases, our model can perfectly emulate the mean prediction of the physics-based simulator, and then also the confidence level, that's the shaded area. The confidence level of these two models also match quite well. So the R0 simulation for this data is 3.1, and we're trying to recreate the scenarios for the COVID-19 area in the early stages. That's in March 2019. So the right plot shows the forecasting mean absolute error versus the percentage of amount data used to train the model. So this is trying to demonstrate the benefit of Bayesian active learning. We're comparing our own acquisition function, LIG in blue, compared to all the other acquisition functions, including random acquisition function, random sampling from the data, or maximum entropy-based method, and mean standard deviation. So just using standard deviation as a way to quantify uncertainty, and then select the samples that with the highest amount of uncertainty. So we can see that our model based on our acquisition function based on latent information gain is most efficient. That actually leads to 68% amount data reduction compared to just training the model with batch training strategy without using active learning. And with this kind of surrogate model, we were able to shrink the runtime from 1 week to 1 day for this US level global simulation. We further extended our work to global level simulation. That's Glean AI, and this is in collaboration with CDC, InsightNet. So InsightNet is this large collaborative research network in the US, and then our team is part of this InsightNet collaborative network. So Glean is the global epidemic simulation model that was used to model epidemic dynamics at a global level. And typically, we would need about 3 hours to generate 100 simulations. And Glean AI is this hybrid deep surrogate model that I just mentioned. It actually only needs 50 seconds to generate 100 emulations. But if you look at the samples from these two models, blue being the physics-based model and on the left, and then the Glean AI simulation on the right, you can see that the trajectories are quite similar. And in terms of the density fitted to the two models, the distribution of these two models also match quite well. So this type of neural surrogate model is really providing a new tool for policymakers and the modelers, and that can accelerate the turnaround time to understand what if scenarios and better design policies for disease control and prevention. So this type of models right now is being used by CDC for seasonal flu modeling, and hopefully we can deploy at large scale. Beyond just training the surrogate model at a single resolution or single fidelity, we also extended this work to capture simulations that are generated at different fidelity, something as known as multi-fidelity uncertainty quantification. Typically for epidemic modeling, for example, we can look at different age brackets. We can group them by a very large age brackets where we have a much coarser simulation, or we can model them at much more fine-grained level, and then we will have a much more accurate but expensive simulation. So this kind of multi-fidelity simulation is very ubiquitous in science and engineering. So how can we develop deep learning models that can quantify uncertainty at different fidelity level? So we have a series of papers at KDD and ICML and trying to extend our previous approach to multi-fidelity surrogate modeling. And here, the active learning algorithm not only need to select from which parameters that we're going to generate simulations, but also which fidelity of the simulator that we're going to query. So there's a multi-dimensional decision-making task that need to be designed for this deep learning algorithm. And then we showed that this multi-fidelity deep learning algorithm active learning framework can accurately emulate a lot of the complex PDE type of simulation problems, especially in the heat diffusion, Navier-Stokes equation, and also epidemic modeling. So recently, our group has moved towards multimodal reasoning. Learning in space and time goes far beyond numerical data. The textual information and the right LLMs opened up new avenues for spatial-temporal reasoning with multimodal data sources. So here is an overview of our Genie project funded by DAPA, where the idea is that we're going to create an AI scientist that can automatically generate a hypothesis using multimodal data sources. So we'll pre-train the model using both numerical data and from simulations and observations, and then combine that with text data in research articles and textbooks. So once we have a pre-trained model, we will fine-tune that for different type of tasks, forecasting, causal inference, scenario creation. In the first part of this talk, I mentioned we will design different models for each of these tasks. The goal of this project is to have a foundation model that can be used for all these tasks in one go. And of course, in order to inject physics into these foundation models, we propose the idea of reinforcement learning with word feedback, where we will use the physical knowledge and simulations that we have to inject physical principles into these foundation models. We have published a series of papers in this direction, specifically about grounding LLMs with physical laws for scientific problem solving, and then also quantify the uncertainty of large language models. To show you an example, here we propose the paper, actually it's on to be at ICML in a couple months, where the idea is we're going to ground these LLMs with physics-based simulations. So the idea is to mimic how a scientific science agents, science scientists work, where they will try to solve a problem first with their internal knowledge. If the problem is too difficult, they will resort to external tools. So we train the LLM agent to mimic that behavior, where the model will first use its own internal knowledge to solve a task, something we call the word knowledge learning. And then when tasks become too difficult, the model will resort to external tools. And in this case, these are numerical emulators that we have built for scientific problems. To interfacing with these simulations, we will use text template-based questions. So we can ask the model to design the shipping route from from one location to the other that will minimize the global average temperature by a certain amount. And we will give this kind of template questions to the model to generate a lot of these paired data. And then we will fine-tune an open source LLM to imbue the model with domain-specific knowledge. And here is the result of our model compared to some of the frontier models, including GPT-4o and Cloud 3.5 for climate modeling and epidemiology modeling. Thanks to our previous research in these two areas, we have very well tuned deep learning surrogate model that can provide very fast and accurate feedback to LLMs. So then our model using this technique can actually significantly outperform some of the frontier models for these two tasks. Another question we're interested is like a lot of people are thinking about using LLMs for time series model, but by nature, these LLMs are designed to handle discrete tokens, and time series data is fundamentally continuous. So is it actually possible to use LLMs, and do they really understand time series data? So we tackle this problem from the task of anomaly detection, and this paper was published in iClear 2005, The idea is we're going to tokenize the time series as a sequence of words, and then we will prompt the model both in terms of just text-based LLMs and multimodal LLMs using VLMs. We generate a lot of the synthetic anomalies, including trend anomaly, frequency anomaly, and point anomaly data, where the idea is that to test different type of hypotheses that the community has established for how LLMs would understand time series data. And we have the following conclusion from our paper. First, for a lot of these LLMs and VLMs, they don't understand time series data. It actually might be better to feed this time series data as images rather than text tokens. We showed in our paper that if you feed this time series as images to VLMs, they get much better performance. And these models also don't have a good numerical reasoning abilities. A typical technique to test reasoning is to use chain of thoughts, but then we showed in our paper that if you use chain of thought, it actually hurt the performance for time series anomaly detection. There's other hypotheses that people have proposed, including repetition biases or arithmetic abilities, or different models have similar performance. So we basically revert all these hypotheses that people had in the LLM for time series understanding regime. So finally, I want to conclude by saying that learning in space and time really requires agents that can reason with physical laws, can navigate complex relationships and data, and can carefully quantify the uncertainty in the data to assess risks. To handle multimodal, highly dynamic, and complex real-world tasks, we need models that is able to handle this kind of high-dimensional situation and being able to process multimodal information. I have presented some of our work at addressing these kind of challenges where I talked about how to inject physics into the model, how to model interactions, how to quantify uncertainty with deep networks. But I believe there's a lot more challenges and opportunities in the domain of learning for space and time. So let me just conclude by showing you these references. You can find all the source code and the data I talked about on my website, and all follow me on social media. And I also want to thank the funding agencies for supporting this work. Thanks a lot.
Thank you very much for Rose's excellent talk. So is there any question from audience?
Maybe you can stop recording for QA, if that's okay.
Yeah, sure. Let me do that.